Swayam Prabha. Digital India. Educated India.
So now we were deriving the equations, and the equations that we had was, this is basically Stokes flow around a sphere, and we have this equation to solve. Okay. In the creeping flow limit. So again I want to emphasize, several books use the del square symbol, which is, and then they use the expression that I have, because del square in spherical actually has a different connotation. Okay. And so you have to understand that maybe the symbol they are using del square for E squared, so that you don't get confused. So now E squared is this plus sin theta okay. So E squared psi will be this thing operating on psi. And what we did was, because of the form of the boundary condition, okay, we seek psi as some function of r sin square theta, because I want this stream function to match my boundary condition at infinity. Okay. This looks like some kind of an ad hoc thing, but we can also do it formally using separation of variables. Now supposing I substitute this inside here, what do I get? E squared psi will be, when I differentiate this 2 times with respect to r, I will get d square f by dr squared sin squared theta. That is the first term, because sin squared theta is a constant, okay, as far as r is concerned, and you differentiate this 2 times sin squared theta, you get 2 sin cos, sin cancels cos, so again I get sin square, right, minus 2f by r squared sin square theta. Okay, that is what I get. So basically I have d square f by dr squared minus 2f by r squared times sin squared theta. This is E squared psi, and this I can think of as, just to explain, I am going to think of this as g of r sin squared theta. Okay, but this is only a function of r. So now E squared psi is g of r sin squared theta. What is g of r? G of r is this. This quantity here is g of r. Now I need to calculate E 4 psi, e to the power 4 psi equal to 0. That means E square of this. So e power 4 psi is E square of g of r times sin squared theta. E square operating on this, because I operate on both sides by E squared. So what I had earlier was f, instead of f I have g. So this is going to be d square by dr squared of g minus 2g by r squared sin squared theta. Okay. So if it is f, I have that, so g, I have this, and g is nothing but that. So this is, can be written as d square by dr squared minus 2 by r squared operating on d square f by dr squared minus 2f by r square sin square theta. All I have done is substituted g equal to this thing again. Okay. So I mean this is just step by step. So you don't have, so it is basically d square by dr square minus 2 by r square whole square, and sin square theta comes out there. So I want to expand this out. So this is d square by dr square of this. So this operating on that, this is going to give me d power 4 f by dr power 4. That takes care of this and this. Okay. Minus d square by dr square of 2f divided by r squared, because okay, so okay, this is taken care of, this is operating on that, minus 2 times d square f by dr squared divided by r squared plus 4f by r to the power 4 equal to 0. Okay. Is this clear how I got this? I mean, these two terms are the second derivative operating on that. This is just this multiplying those two. Okay. And I need to evaluate this. I need to differentiate this 2 times. So you should do it. I will also do it, and hopefully our results are going to match. So rather than write that stupid thing, fourth derivative, so f4 is just fourth derivative. Okay, I am doing d by dr minus d by dr of differentiate this once. What do I get? Using the product rule, 2f dash by r squared minus 4f by r cube minus 2f double dash divided by r squared plus 4f by r power 4 equal to 0. Okay. So at this again I have to differentiate this thing by product rule again. So I am just doing differentiation, we can do it. So fourth derivative minus boy, I keep the minus outside. Okay, 2f double dash by r squared minus 4f dash by r cube, again minus 4f dash by r cube plus 12f by r power 4 minus 2f double dash by r squared plus 4f by r power 4 equals 0. So I mean you can do this peacefully, and now you just group all the terms together. Fourth derivative, I don't have any third derivative, I only have the second derivative. I have minus 2f by r squared, 2f double dash minus 2f this thing, so it is minus 4f double dash by r squared. Then I have minus 8f dash by r cube, minus and minus is plus by r cube. Okay, and what do I have? Plus 8f by r to the power 4 equal to 0. So basically this f of r, which I assumed as the r dependency, has to satisfy this differential equation. If it satisfies this differential equation, then my psi is a possible solution. Okay, and then of course I have to worry about the boundary conditions and all that. Okay, so what have we done? We got the fourth order equation e power 4 psi for the stream function, and then we are trying to find the solution by saying it is f of r times sin square theta. Okay, and in order for that particular form to be a solution, it has to satisfy the differential equation. So, I just substituted it in the differential equation and I proceeded, and I say f has to satisfy this. So, basically f has to be a, and this of course is multiplied by sin square theta. Sin square theta cannot be 0, because if sin square theta is 0, I have a trivial solution, psi is 0 everywhere. So, this has to be 0, okay. So, that is an important point which you should remember. So, f must satisfy this equation, and you look at this equation and it says, and this is what is called some Euler form or Euler Cauchy form, and we seek this is, I think different people call it different names, Cauchy form, and the solutions for this are of the form r to the power n, f of r as some constant times r to the power n. So, with the fourth derivative, what do you get? N times n minus 1 times n minus 2 times n minus 3 times a r to the power n minus 4. Then I have this minus 4 times, what is it? F double dash, right? N times n minus 1 times r to the power n minus 2 divided by r squared plus 8 f dash, I think, times n to the power n minus 1 divided by r cube minus 8 r to the power n divided by r to the power 4 equal to 0. And I think there is an a everywhere. This is an arbitrary constant. Okay. So, basically the point I am trying to make here is I can factor out a r to the power n minus 4 and n minus 1 into n minus 2 multiplied by n minus 3 . So, basically r to the power n will be a solution if this quantity inside the square brackets is going to be 0. So, basically I have a fourth order equation in n, right, 1, 2, 3, 4, I have fourth order equation in n, so I have 4 roots, okay. So, basically n must satisfy this term in the square brackets equal to 0. And you can find what the roots are, okay, and the roots are integers. I remember these roots. So, n, the 4 roots minus 1, 1, 2 and 4, okay. So, these are the 4 roots this has to satisfy. So, basically what I am trying to tell you is that the stream function psi is of the form a divided by r to the power minus 1. So, a divided by r plus br plus cr squared plus dr power 4 sin square theta. This is psi, okay. Psi is of this form, some function of r multiplied by this, and we found out this particular form satisfies the differential equation, okay. Now, what I have used different constants because I need to keep things general. I can't assume all the constants are equal. If they turn out to be equal, they are equal, but I need to keep things general. So, all these constants are basically different. We need to find these constants, right. I mean, I got my psi. So, idea is I have psi. If I can find these constants, I can find the velocities because I know how velocity is related to psi, okay, and then you can proceed further. But how do I find these constants? I look at this as r goes to infinity, psi must satisfy, what did we have, u infinity r squared by 2 sin square theta, right. This is what we said yesterday. I think this is right. Okay. So, I look at this thing, as r goes to infinity, this guy is going to go to 0, this term is not going to contribute. Okay. This term will also go to infinity, but r squared will go to infinity much faster. Okay. So, compared to r squared, this will be not contributing much to the stream function, because you take larger value of 10 power 5, 10 power 10, this will be only 10 power 5, this will be 10 power 10, okay, and this will be 10 power 20. So, this will be much more dominant. So, the point is, as r goes to infinity, this will definitely not contribute, this will contribute less than this guy, and this will contribute less than this will be dominant. But I know that my r dependency has to be r squared, it is not r power 4. If this is going to be present at r going to infinity, this will start dominating. Okay. So, r power 4 will be dominating, but I do not have r power 4, I only have r squared. So, I conclude that d has to be 0. Okay. So, since psi dependency is r squared as r goes to infinity, d must be equal to 0. Okay. Else the dependency, if it is not 0, will be r power 4, okay, that will dominate. The other thing is, I need to find, so this goes off. Okay. Now, I want to make sure this guy is going to match this. So, I can compare as r goes to infinity, these two will not contribute much. Okay. This is going to be r goes larger and larger, this will be very, very small compared to that. So, I just need to, I can calculate C by saying that as r goes to infinity, it should be C r square sin square theta must match u infinity r square sin square theta. Okay. So, as r goes to infinity, u infinity theta by 2 equals C r square sin square theta, and so C is u infinity by 2. Okay. So, I have been able to find two constants making these arguments. I need to find now two more constants, and those two constants will come by using the no slip and the no penetration conditions at the wall. Okay. So, and I am not going to do it, and this is the thing, now you guys have to do the work, because I think so use jumping, oh man, I erased this. Anyway, use psi equals 0 at r equals, what was the radius of the sphere yesterday? Was it r naught or a? A, yeah? At r equals a, surface of the sphere, and d psi by dr equals 0 at r equals a, surface of the sphere, to find the other two constants a and b. Okay, that you will do. So, now you know what the stream function is. Okay, you know, so we know stream function psi. What was it? A by r plus br. C is known, no? C is u infinity by 2 r squared sin square theta. Now that I know the stream functions, so you will do this, calculation, but I mean, I respect your ability to find integration constants. Okay. So, you will find this, and by the way, this is a very standard thing. So, you can, after finding the constants, you can verify it in any standard book. maybe Bert Stewart Lightfoot or Gary Leal, or in the internet there are so many places where this particular thing is discussed. Okay. So, you can do this and make sure that the constants you are getting is indeed the same. I need you to get habituated to doing these derivations and finding these constants. So, you will get confidence that you can do these kind of problems. There is no point in me doing everything on the board. So, do the thing, find the constants, and you can easily verify with this information available in the internet, okay, or in any book, standard book. So, now we can find Vr and V theta using the definitions of Vr V theta as a function of psi. Again, I'm not expecting that you will remember all this and all that. The idea is today we live in a world where everything is available on the internet. So, you need to know how to do the problem, okay. It's not that I expect you to remember. So, I'm not going to sit here and say that you have to memorize. The information is given, you need to know how to use this information to proceed and solve a problem, okay. So, you have the standard definition Vr is 1 by r square sin theta, whatever, d psi by d theta, V theta something. So, now you can actually calculate Vr and V theta, okay. So, I now know the velocity field. What is the thing I do not know? I do not know the pressure, okay. I need to get the pressure field now. So, so far what have we done? We have got the velocity field Vr and V theta, which will satisfy my creeping flow equations. It will satisfy my boundary conditions on the surface of the sphere and far field boundary conditions, okay. I can find, because I eliminated pressure in the process of trying to do the stream function, okay. How do I get pressure? Force and area. Force and area gives you pressure, but that is correct. Force per unit area gives me pressure, but where was pressure initially present? It was present in the Navier-Stokes equation, okay. The Navier-Stokes equation is minus, what you are saying is right, pressure is force per unit area, but I need to find the force. I can't go backwards. From the pressure I want to find force. From force I can't get the pressure because I do not know the force yet, okay. Minus gradient of P plus divergence of tau equals 0. This is the creeping flow equation, okay. Tau, remember we are talking Newtonian fluids, keep life simple. Tau is going to be found in terms of gradient of V, mu times grad V plus grad V transpose. You know V, you can now calculate what it is, okay. So, you can substitute. So, you have two equations here, minus dP by dr plus something equal to 0 minus 1 by r dP by d theta or something like this equal to 0. Two momentum balance equations are there, right. You can use any one of them. Now, you know this is a function of velocity, this is a function of Vr V theta. Again, Vr V theta, because we live in this world of internet and everything, this is available to you. Go to the internet, okay. Go to the internet, look at the r momentum equation and the theta momentum equation in spherical coordinates. You can choose any one of them. You don't have to do, you don't need to do both, okay. So, now you let us say you take the r momentum equation. I already know Vr and V theta, okay. So, I can substitute it here, I can simplify. I mean, after all it is only derivative. So, you differentiate first two times, 3 times, whatever the expression is, you calculate it, okay, and you will get some expression in terms of something, and then you can integrate this expression from infinity to any radial position r. And in far away, I am saying you have a constant pressure P infinity, okay. I do not know what it is some reference pressure P infinity. So, basically what I am saying is 1 and 2, we can use either 1 or 2 I have 1 or 2, say we use 1, okay. Then I have and integrate it from infinity to r. So, minus dp will be some function of r and theta, okay, times dr integrated from if it is p infinity here, that corresponds to r equal to far away. So, the lower limit will be infinity, and if it is the surface here, no, if it is the surface here, it is or some arbitrary p, it is some r. Okay. So, I get the pressure field because it has to satisfy the Navier-Stokes equation. I am just calculating the pressure field, so it satisfies that. So, now I know the pressure field. Okay. So, basically the things that I wanted to do, find the velocity and the pressure field, have been found out. I am now in a position to find what the force is that is acting on the sphere, okay, because all the information of what is the velocity field, what is the pressure field is known. So, now again you have to do it, I am not going to do it, and you can also verify it from the literature, from the books, because I mean I don't have to prove to you that I know how to differentiate. You have to prove to me that you can differentiate and integrate, right? Unfortunately, that is the way it is. Okay. Now, what is the point? I have the sphere. I had things flowing down vertically yesterday, and what is going to be the contribution? What are the things that are going to be contributing to the force? The drag force, remember, is defined as the force which is acting in the direction of the flow. Okay, that is how the drag force is defined. So, F drag, and let us say this is Z, okay. F drag is defined as the force acting on the sphere in the Z direction, because that is the drag force, okay. Because force is a vector, I mean I am only interested in the component which is in the direction of the flow, that is the definition. Now, therefore, I want to find out what are the things which are going to be contributing in the direction, because I have to, the total force acting on the sphere may not be in the direction of the flow, but only the component which is in the direction of the flow I am focusing on, okay. So, anyway, now if you take an area element here, okay, we will calculate now the area element for a spherical coordinate system is defined as r d theta r sin theta d phi. That is your area element, that two azimuthal angles, okay. And again you should know this how it is defined. One way to check that this area element is right is you can integrate this as r goes from, so to find surface area of the sphere, what would you do? I would just do a double integral d theta going from 0 to pi and d phi going from 0 to 2 pi, because the extent of theta is from 0 to pi, and so this is the area element and r is my area of the sphere, r is a, okay. So, this is a d theta is there multiplied by a sin theta, right. I am putting r is a because that is my surface area, I mean that is my radius of the sphere, and I am interested in the surface area. Okay. So, this turns out to be a squared, there is nothing which has phi in it. So, integral from 0 to 2 pi will give me just 2 pi, and integral of sin theta d theta from 0 to pi will be something, okay, has to be 2, so this will be 4 pi a squared. So, what have I done? I am just trying to justify that this form is correct. So, when you get something, you have to make these cross checks to make sure that this area element, when I am integrating over, so I took a small area element, I integrated over all of theta and all of phi. When I do that, I must get the area of the sphere, which is what I have got. Okay, you can do that integration. So, now I need to find the force. If you remember what you did earlier, there are different components on the sphere. That is this pressure acts normal acts in the inward normal direction to the surface. I mean, if we have a sphere which is stationary, one way to understand this pressure is look at all the molecules which are going to come and bombard against the sphere surface. These molecules come bombard and they will get reflected. So, as far as the fluid is concerned, it is going to, the fluid molecules are experiencing a force in the outward normal direction. As far as sphere surface is concerned, it is going to get the reaction force, which is in the direction of the inward normal. Okay. So, that is the reason I am saying pressure is in the direction of the inward normal. Now, what are the other components which can give rise to the force? If you remember your shear stress that we spoke about, whenever we have fluid flowing, you on this surface you will also have, let me draw this thing, this is the radial direction. I am interested in the normal component coming from the shear stress, normal component from the viscous stress, that is tau r, and our thing was tau r is positive when it is pointing outward, right. The radius is in outward normal direction, tau r is positive if the stress is also in the same direction, only then tau r is positive. Okay. So, there are two contributions coming for the normal stress. Okay. So, the two contributions from the normal stress, which is minus P plus tau r. I am putting a minus sign because tau r is positive in the outer normal direction, P is acting in the inward normal direction. And if you remember your Navier-Stokes equation, we have minus P plus tau. Okay. So, that is the reason we have minus P, and I can write the entire thing in a matrix form. The normal components will always have minus Pi, minus P plus tau. Okay. So, anyway, that is the normal component. Is there going to be any other contribution? In the r direction, the surface outward normal is r, this is the outward normal r. You also have the phi direction and the theta direction, tau r phi. This will be 0 because we are assuming phi symmetric. Okay. And only tau r theta will contribute. Okay. Tau r theta will contribute. So, this is the force which is acting in the theta direction. This is the stress component which is acting in the theta direction on the surface of the sphere. Okay. So, both of, and this is in the theta direction. So, this will also have a component along the direction of the flow. This is acting normal to the surface. Every point this is acting normal to the surface. So, what I have to do is I have to resolve it in the vertical direction. Okay. I have to resolve that in the vertical direction, and then I have to integrate it over the area. Then I get my force. I mean, that is the concept. Okay. If I take an area element here, okay, just to explain to you, and this is the normal direction, and this is theta angle. Okay. The what is going to be the vertical component of this force? The normal forces will contribute minus P plus tau RR times what, sine or cosine. This is theta. Okay. This angle is theta, alternate angle or whatever. So, this cos theta. Okay. And tau r theta, remember, is defined like this, and is tau r theta, and if the normal component is cosine, tau r theta has to be sine. Okay. So, the tangential force contributes, I should not say tangential force, I should say yeah, contributes, normal force contributes. This is the contribution to the drag. Okay. The cos theta component is the contribution. This is the, therefore, it has to be sin theta, tau r theta sin theta, and this is positive. Okay. I want it in the vertical direction. So, what is it going to be? So, this is going to be sin theta plus or minus, that is the question. Okay. So, this angle is theta. So, then this angle is theta. So, this sin theta. Okay. And minus P are resolved in that way. So, it will be tau r theta sin theta. Okay. You can check with plus or minus. Now, I just want to, how do you go about finding the force? You have to integrate this over the area element. This is the stress, force per unit area that you are talking about. Okay. Pressure, force per unit area, this force per unit area. So, to find the total force at a specific r and a specific theta and a specific phi, this is the value. I have to integrate it over the entire surface area. So, to find the force, minus P plus tau r cos theta times A d theta A sin theta d phi, because I am interested in the surface of sphere, r is equal to A. Okay. And this is theta goes from 0 to pi, and this goes from 0 to 2 pi. Phi goes from 0 to 2 pi. Okay. So, this is the area element plus the other guy 0 to 2 pi, 0 to pi, tau r theta sin theta A d theta A sin theta d phi. Okay. This is again area element. What I am, so you know how to, we already found the pressure, you can find the tau again in terms of the velocity components. You already found the velocity field, so you differentiate it from the expression tau r and tau r theta. There are standard expressions available. Tau r is dur by dvr by dr multiplied by 2 mu. Okay, that is straightforward. The other ones are not so straightforward. So, you will get that. If you integrate this, you should get the force as 6 pi mu A u infinity. So, this is basically how you go about calculating the drag force on the sphere, and this is valid only in the limit of the creeping flow. Okay. This is, I am just wondering if it is a plus or minus sign. Okay. You have to resolve that. Drag force in the creeping flow limit. Any guess as to when this drag force was actually calculated analytically by Mr. Stokes? Somebody has to guess the year in which this drag force was derived. You have to guess a 4-digit number. It has to be less than 2025. Yeah, it can't be more than 2025. Yeah, so it was almost 200 years ago, 1850. Okay. So, what I have derived is nothing new. It is a story which is almost 200 years old. So, those days, of course, people did not have computers, they did not have WhatsApp and mobile phones. So, they had a lot of time on their hands and they were pretty jobless. So, they were worrying about these kinds of problems, and they were able to actually solve and get some do some calculations. And you see, calculations are basically by hand. Okay. I mean, I could have derived spent one more class deriving the velocity field, but there is no point in me doing that. Okay. So, the point is, you can actually, you need to get comfortable with doing these analytical calculations, the derivations and the integration. I am just giving you what the basic idea is, what are the arguments made for dropping a term or keeping a term. Okay. But that I think is something which is my job, but actually doing the differentiation, actually doing the integration is something you have to do, and you should be able to do it now, I mean, on the basis of what I have said. So, my expectation is that you will sit and do this calculation and verify that this is indeed Stokes' law which you get. Okay. You just check the sign. Okay. It is plus or minus. Now, I will leave that for you, to you people. So, like I said at the beginning, what we have done is, because it is in the creeping flow limit, because this is the creeping flow limit, because I have a linear equation, okay, we could do this since we are in the creeping flow limit and the equations are linear. Okay. Now, if you are not in the creeping flow limit, if your Reynolds number is large, okay, if Reynolds number is large, we cannot use this. Okay, this expression for drag force cannot be used. And then what you do is, you have this charts which you must have used in your undergraduate somewhere, some curve like this, and for a particular Reynolds number, as long as you are in the low limit, this is a log plot. So, the slope is -1. Okay. So, this slope is -1. So, you can do some experiments, calculate what this drag coefficient is, and then you can calculate what the force is. So, this is basically has a limitation that is valid for Reynolds number small. If you want, you can extend it to some extent and maybe try to push your luck, but for large Reynolds number you can't use this. Okay, keep that in mind. And yeah, so that's it as far as the Stokes thing is concerned. Stokes drag force is concerned. You should you should derive this. Okay, I have given you all the steps, and I need to see this working of the steps. Okay, and I think you will become more confident about doing things. And like I said, several books have all the intermediate steps also, several places. So, you can just take a look and you can check whether what you have done is right. Okay, thank you.